Hi, everyone. Welcome to the day 3 of LLM Context Engineering Bootcamp. Before we start, can you please confirm if you can see my screen and hear me and see me all right? Awesome. So yesterday's session, I have scheduled on YouTube for today IST 3 p.m. So the link should be accessible by then. I have posted it on the course dashboard also for students in the free plan. So we can get started. So where we stopped yesterday was discussing how to structure the cloud.md document and how the system prompts work. We discussed how when you are passing the context into the large language model, that the entire cloud.md is not passed, but rather a portion that is relevant to the current query is being passed into the prompt. And this tremendously reduces the token consumption due to the, let's say, claude.md or agents.md files. Those files can, typically they are maybe 250 to 600 lines or something like that. But in case they are so big, if it is like 5,000 lines or 3,000 lines, you don't want to be loading that all the time. And we also discussed that to fetch the relevant sections from that document, you may use keyword matching or you may use RAG. So although we discussed briefly about RAG yesterday, we did not go into the details of RAG, and that is what we are going to do today. Today, all of us together will be coding a RAG chatbot completely from scratch, which should work on almost any kind of document. So along with that, we will also be discussing about the right part of the write, select, compress, isolate framework. So specifically, today we are discussing two parts of the write, select, compress, isolate framework, which is write and select, out of which RAG belongs to select, because select means you are selecting what should be there as part of the context at any given point of time. Write means if you want something to be part of the context sometime later, but you don't want it right now, you write or you store it in the memory, either in a persistent memory or in a temporary memory. So we'll briefly discuss that also, but primarily most of today's time we will be spending on coding RAG-based chatbot, which we will do in Google Colab, so that every single one of you should be able to do it with me. And we'll be writing almost every single line of code. So this is the idea behind write, select, compress, isolate framework. It's part of something that LangChain had defined originally. So here the main focus is on the context window. So in perspective of context window, write simply means you move something out of the context window, you store it somewhere so that later you can retrieve it if you need it. Select simply means you are selecting some things specifically from your storage to be part of the context window for the time being. So it's a dynamic process. And this is where RAG comes into picture, because RAG means you are retrieving some things from your database to be for that to be part of your context. Isolate is where agents or tools may come into picture. Isolate meaning you are splitting the context or you are providing an entirely new context for a separate API call to be made, so that if there are sub agents defined for subtasks, you don't want the context of those agents to be polluted by the context of your overall task or overall execution of what you are building. And compress is if your context window, let's say, is 80% full, that means you only have very little space for the upcoming tasks. So you need to do something with the context window, which is 80% full. And what you could do is either you can completely clear the context window, which means everything is lost. That is not very good. But a better thing to do is you can simply compress the context window. So you compress such that everything that is taking, let's say, 50K tokens, you represent in a summary using maybe 5K tokens. So you save a lot of space in the context window, and that space can be used for producing better quality output. Yes, it's very much like /compact in Cloud Code. /compact also does the same. /clear is different. /clear clears the context window. /compact compacts the context window. But in Cloud Code and many other coding agents, compacting is already part of its framework, meaning by the time a certain threshold level of context is full, it performs auto compacting. But sometimes you may want to compact yourself when you are building, when you feel like your quality of whatever you are trying to generate is degrading. You should feel like, oh, it's probably time to either clear my context or compact my context. So today's 80 to 90% of the time will be spent on this RAG. Little bit of time we will spend in figuring out what exactly will we write if we are moving something away from context window for later usage. So yes, so isolate is nothing but if your context window has 200K tokens, and if so much portion of this context window is full, a better thing to do is have a separate isolated context window where none of these tokens are present. So none of these tokens, which are part of your main context window, should be present in this isolated context window. And this isolated context window will make a separate API call to your, this isolated context window will be used in a separate API call. And where is this used? Let's say this is your context window of the main task. And as part of this main task, let's say you are working on certain experiments and you want to analyze the result of some past experiments. You don't want the main task tokens to pollute your subtask. Your subtask is just analyzing the results of an already done experiment. In that case, you can create a separate isolated context for your sub-agents, and sub-agents will make its own API call. And that context window associated with the sub-agent will have only information relevant to this, right? So we don't have to, we can create sub-agents by just mentioning it explicitly. If you want to spin off sub-agents, you can mention it explicitly if you are working in Cloud Code. But if you are not explicitly mentioning also, sometimes you will notice that Cloud Code will by itself decide to spin certain sub-agents, right? So isolate, we will be coming to that. Isolate as in dealing with tools and agents, we will be coming to that tomorrow. Tomorrow's main task is working on MCP. And today it will be, okay, there is one question, how the context will be shared across sub-agents and parent agent. So there are files which are shared across sub-agents, which will be accessible to both. So whatever is put in storage, so the storage, some of the files are commonly accessed irrespective of what sub-agent you create. For example, the agents.md file in the top of the hierarchy, cloud.md file, which is also in the top of the hierarchy. Or sometimes from your memory, there are some persistent information which you want to make available for different agents. So it is within the agents.md file, you can define where it can get the relevant information from. This can be done manually, but because Cloud Code is so smart, when it defines agents.md itself, when you ask it to do it, it will automatically mention that in the agents.md file. If you remember from yesterday's example, I first had created ideas.md, which was raw. Then I had created ideas v2.md, right? And then based on ideas v2.md, I asked it to create a cloud.md file. And if you remember, in the cloud.md file, there was a reference to ideas v2.md, and that was automatic. I did not mention it explicitly. Similarly, in agents.md file, you can have reference to other files, and this agents.md file could be, let's say, agents.md for agent number 1, sub-agent number 1, and agents.md for sub-agent number 2. Both of these MD files can have reference to common files, and it can share information. And that information, if it's in a compressed format, will be part of the context of both of these subagents. So there are actually 3 types of things which you typically store in the storage as part of write, right? So one is short-lived. Ephemeral means short-lived context. So short-lived means if you have 3 phases in which you are building your product. So when I'm building the email, the news aggregator agent for AI, I have a short-lived context as well as long-lived context. Or if I'm building an email reply agent, I have short-lived context and long-lived context. Short-lived context is something more like the current thread which I am referring to. So if I have a current thread, and if I think all the information in the current email thread might be relevant, to whether craft a new reply in the thread or to craft a new email in the thread. But if I don't want to store it in the context right now, I can simply put the current details of the current thread in a file, which is temporary, and then refer to it later. And this temporary file can also be, I'll show you one example. It can be I'll come back to this in a second, but you can define a temporary file called task.md. Yes, context window is ephemeral for sure. But often what happens is the tokens that fill the context window from one API call to another API call, sometimes 60% of 50% or 60% of those tokens can be the same. And why is that? Simply because the markdown files which define your primary task are the same. Maybe the result of two different tool calls have very high overlap. So because of that reason, although two API calls are distinct, the way in which tokens are populating your context window, you may find similar tokens in two different API calls context windows. 200K number, is it deliberate or random pick? Found at multiple places that 200K is a sweet spot. Yeah. So 200K is something which is routinely coming if you have a 1 million token context window or 2 million token context window. Your the amount by which you can fill the context window is not like entirely 1 million or to 2 million. Just because the LLMs are providing bigger and bigger context windows, it doesn't mean that you should be filling it to 80% of its capacity. The most recommended size for these kinds of context window is 100 to 200K tokens, because otherwise context rot will happen. You may be only filling like 50% or 60% of the context window, like 500K tokens or 600K tokens, something like that. But that itself can cause context rot. One thing you should realize is, I have a question. Is context window only for the input to the LLM, or does it also matter for the output produced by the LLM? Context window, does it consider the tokens for input or output or both? It actually is meant for both. Context window actually consists of, that's the reason why when the LLM produces an output, right? You have to leave some space in the context window for the output to be stored. Otherwise, your output will be truncated because the context window will get exceeded. And in any case, the output is produced using next word prediction in most of these models. Output is produced auto-regressively. So next token is added to the current set of sequence of tokens. Using that, the next token is produced, and so on, right? Then, okay, there is a question. What's the logic behind using files to store this information rather than some database? So yes, so in RAG, if you are performing RAG, you will be storing all the files in a database. Otherwise, there will be huge latency. But you know what? Sometimes I have noticed, so this is my experience, okay? So I'm building this email reply tool. And we were discussing, maybe because of the sheer volume of emails and the sheer number of different programs that we have, we should probably have a RAG system to fetch the appropriate details about the programs and appropriate details about the past emails using a vector database, okay? And then we implemented it. But to my complete surprise, I noticed that the performance was even better by completely abandoning the vector database and just defining a markdown document with around like 600 or 1000 lines, which was a sort of like a proper summary of these both documents, which describe the details of our program and that describe the details of our past emails. We also recently built a voice agent for calling. So for example, if somebody wants to make a phone call and understand some details about what we do and everything, we just created an agent with a US phone number. You can call that agent and you can talk, and the quality of the output from my experiments, I saw that it was so good, and latency was not at all that much of an issue. And there, the only knowledge base was a properly written markdown file. I don't remember it was a markdown file or txt file. I have to check that once more. But it was literally, the knowledge base was one properly written document with appropriate links if needed. But so from our experience, yes, you can do RAG, and in theory, it should work better than having just files, both in terms of latency as well as accuracy. But from my experience, it has been, at least in the recent times, it has been the reverse. The simpler, the better. That was the case. But I'm not saying it's a rule or anything. I'm just sharing my experience. Then if you are, so basically, if you are performing a phase one implementation of a website building, in the website building, currently you are, let's say, working on a specific card, a card to display information. This is one subtask. And if you need some information which you might use for making a card in your website in the later part of your API call, then you may store that information as a in a task.md file like this. So these task.md files are defined for as something like a scratchpad for the current task. It's not meant for the uh, whole session. It's meant for a particular subtask. And just like how humans use scratchpad, this you might have also noticed when you run cloud code in the terminal also. In the terminal also, it creates these things to check. So different tasks will be defined and you can check them off. So similarly, you can explicitly mention like the agent to define a task.md file. Task.md will define the to-do list, and this to-do list will keep on getting updated with what is done and what is to be done. And this is completely temporary. This is never used. And why is this useful, by the way? The reason why this is useful is your overall project, you might have realized that you can describe it in two phases. Phase one is single user experience. Phase two is multi-user experience. Phases equal to 2. But then within the single user experience website, there are many different subtasks which you may want to implement separately, because implementing this whole phase one is difficult. Implementing this whole phase two at once is difficult. So what you really want to do is within phase one, you may define phase 1A, phase 1B, phase 1C, and so on. Okay. Phase 1D and so on. And when you are implementing phase 1A, you want to keep track of two things. One is what your overall goal is. The overall goal is the fact that you have two phases. In phase one, in general, you are building this. Next, you have to go in general to phase two. And this will be generally stored in the cloud.md file, which will be accessible anyway to the sub agent if needed. But the details of what is being implemented in phase 1A, you don't have to have a permanent file. You can simply have a task.md file, which the agent will itself take care of. And the task.md file will keep on getting modified within the implementation of phase 1A. And for phase 1B implementation, there will be separate task.md file. So this is one way in which you can have short-lived memory. And from that memory, context window can pull information whenever needed, or context window can store information to that memory whenever needed. Just a second. All right. So there is a very specific way in which you can think when you will need to write something, and whether it should be in the transient or whether it will be in the persistent context. So basically, if something is going to be used in the next 2 minutes or 5 minutes of implementation, it will most likely be temporary. It will never be used again, and it will stay as these task.md files. But if something is transient, for example, if some files are being referenced in the agents.md folder for the sub agent, not for the entire task, but let's say a sub agent has an agents.md file, and this agents.md file is referring to a specific set of files or a specific database. Okay, only for that task, but then it may be referenced throughout the duration of that particular task, which may last not just 5 minutes. It can last for half an hour. It can last for 2 hours, depending on the time span of implementation. Then those are a bit, it's not a completely short-lived. It's like a transient context. And those files you will probably be, it will again be, it could be MD files or it could be vector databases, depending on what the complexity of your task is. If it is a vector database, you will be for sure implementing RAG. If it is a text file, you could be implementing either RAG or typical keyword matching like TF-IDF. We will come to TF-IDF in later part of today's lecture. And then if it is an enduring context, which you don't want to store in the context all the time, but you may refer to it every single time, This is something which you will store in your global workspace. It won't be part of the sub-agents. It will be part of your cloud.md file. It may be referred to the cloud.md file, just like the ideas v2 document. Ideas v2 document was referred to in the cloud.md file throughout the implementation of the project, because that is part of my entire project's philosophy. So this, we will not be discussing too much about compress and isolate right now. We will discuss mostly about the select, because this is the probably the single most important concept that you should be familiar with. All right. So yeah, so just have a look at this. If something is to be used for just 5 minutes, look at task.md, which is scratchpad, ephemeral, short-lived. If something is used in the next session, so let's say you are running cloud code in the morning session and evening session, but you are still working on the phase 1A implementation, you will most likely need something which is used in phase 1A in the morning and phase 1A in the evening. In that case, you could store it somewhere in DB files or user preferences as markdown files, any kind of format, whatever is convenient for you, because all of these anyway cloud code can access, whether it's in a vector database format, or whether it's in a structured document format like XML or Markdown file. Cloud Code can access any of that. But for example, if something is not at all short-lived, something that is going to be universally used, to give an example, we are also building like a central brain for our company. So the central brain will be like an orchestrator, okay? And so individual orchestrator. Okay, so individual developers in our team are building separate agents. So this is, let's say we call this as agent number 1. This is not sub agent. These are separate projects in the themselves. This is agent number 2, and then this is agent number 3 and 4. Okay. Now, one concern that we have right now is, right now we have no way to connect agent 1, agent 3, 2, and 4. All right. Right now, this agent, the task that this agent does is completely isolated compared to task that agent 2 is doing. So now what we are doing is we are building a two-way MCP, two-way model context protocol, where this agent 1 can communicate here, as well as central brain can communicate here. And so can agent 3 with central brain, 4, as well as 2. And the central brain can act as the orchestrator to say, hey, you do this agent 1, and once that is done, agent 4, you do this task. But then here, certain files need to be commonly understood by the central brain orchestrator. Those files will invariably be the cloud.md files in each of these agents, which are defined separately. These are, please don't confuse this with sub-agent. This I'm talking about 4 separate projects. In fact, 5 separate projects. This is project 1, project 2, project 3, project 4, and project 5. Project 5 is just an orchestrator agent where it won't be doing any task by itself. It will simply be asking other agents to execute tasks, but to know what the core philosophy and core implementation strategy of each agent is, these files, cloud.md files, will be referenced to again and again and again. If there is any database, let's say one of them is an email agent, it may have an email database stored in a vector database that will also be used again and again and again. So the time span of such documents will not be few minutes, or it will not be few hours. The time span of those documents will be few weeks or few months, and they will be stored in cloud.md files or in any other format. So this is ephemeral memory, this is persistent memory, and this is a bit more short-lived. It can be called as transient memory. But if something is used only once right now, you don't have to store it. If something is used only one time in a context window, don't save it or don't store it, just use it and you are done. You just forget about it. Now, since we will be spending at least 45 minutes or something today coding, okay, there is a question, but why can't we directly connect each project through two-way MCP? Abhi, I guess you're asking, why can't agent 1 and agent 2 be connected? Is this what you're asking? Yeah, it can be technically done, but the thing is, agent 1 is, let's say agent 1 is good at doing research, okay? And agent 2 is good at communicating through emails. The problem is agent 1 does not know unless told, hey, this is the overall, these are the projects that we are currently doing, and these are the tasks that are pending, and you should be doing this. So agent 1 does not have an overall idea about our central brain of the company. It does not know overall in our company what all things are happening. It is only focused on that one task. Same thing for agent 2. Agent 2 is only good at one thing. If somebody asks it to, let's say, craft an email, it will craft an email appropriately. But it does not know anything else. It does not know when to do something or whether to schedule something or not. For that, you need to provide instructions. Execution it will do, but instruction someone else has to provide. And that entity who is best to provide such instruction is an agent who acts as a central agent who will have access to all sorts of information in the network. So this agent will not be provided with any tools to actually execute the central agent. Central agent will only be provided tools to access information and delegate it to other agents. But technically, yes, it is possible to connect two different agents through two-way MCP, not a problem. But I don't think it's a good approach. Okay, now let's get into retrieval augmented generation. And this is a very, very interesting topic and maybe one of the most important topics that you have to know, irrespective of what industry you are working in. And this will, I think if you master RAG, you will, lot of issues you will be able to solve for other companies. So when we work with other industries, so we have a division called First Principle Labs. I don't know how many of you are aware of it. So this is our website. So we partner with a lot of industries for solving their actual real world challenges. So you can read about our work. But the point is, most of these projects that we have worked on have something to do with building a RAG-based chatbot or RAG-based retrieval system, either for internal company purposes or for external customer facing purposes. So from our experience, and it's not easy, right? RAG, there are easy ways to implement RAG, which is what we will be doing today. But there are also complex databases where retrieval is actually difficult. So many companies are actually having this requirement of wanting to implement super efficient, highly accurate RAG pipeline for their internal purposes or for customer facing purposes. And if you can master that skill, I think you will have a lot of value to provide to the industry. So RAG, in simple words, it's retrieval augmented generation. So what is generation? In large language model, it produces next token output. So that is generation. And what is augmented generation? Augmented generation means you are providing certain prompt to the large language model, but that prompt is getting augmented by something. And what is that something? That something is a retrieved document. So basically, when you provide a prompt to the large language model, that prompt get appended or prepended or augmented with a retrieved set of information from a database. So this is the reason why it's named as retrieval augmented generation. Now the basic philosophy behind this is very simple. You know about the cost of training a large language model from scratch. It is very expensive. The cost of fine-tuning a large language model on top of pre-training is also, it's not as expensive as pre-training, but it is also kind of expensive. Fine-tuning is not something which you will do every day. Now, what can you do to make your large language model access information which it does not know, but which are there in other documents? That is where RAG comes into picture. So today we will discuss all of these individual steps that are part of RAG, and we will actually implement it. But let's look at what RAG does. So let's say you have a PDF document. So the example that we will be taking today will be a document which I have downloaded from Microsoft, I think 2025 shareholder report or something like that. So that document will be like a 98-page PDF document. So how did I create the PDF document? I simply did Control P from their website. So their whole web page of their shareholder report was printed as a PDF document. So first we have to ingest the PDF document. So ingesting meaning the PDF document will have text, tables, images, links, etc. And this has to be somehow ingested by some library, and it should be stored in a certain format. That certain format will almost always be a text format. Sometimes it will be an interleaved format with text and images. Sometimes if you use a optical character reader, OCR library, you will have a slightly different format. But basically, you should be ingesting the document before you do anything with it. Then what we do is we do something called as chunking. Chunking is you split the document into different chunks. A way in which you can imagine this is, let's say you have written a 100-page essay. This 100-page essay has different, let's say, different sections. Within each sections, you have different paragraphs. Within each paragraphs, you have different sentences. So chunking can be in different ways. You can say, I will define one paragraph to be one chunk. Or you can say, I will define one sentence to be one chunk. Or you can say, I will define one meaningful part of this document to be one chunk, another meaningful part to be another chunk. So chunking is literally splitting the document into different parts. And then what we do is we convert these chunks into vectors. When I say vectors, literally just this multi-dimensional vector. A vector is just something that lives in a multi-dimensional space. So it will not be two-dimensional vector, but rather it will be a higher dimensional vector like 384 dimensions or 724 dimensions or whatever the embedding model allows. So each chunk will be normally represented as one vector. So if you have 500 chunks corresponding to a document, you will have 500 vectors, and these 500 vectors are now storing the entire information present in your whole PDF document. And you have to store the document in such a way that you should be able to access it very quickly, right? Because the whole point of storing this is for retrieval later. So there are different databases like Chroma database, Pinecone, etc., which we will discuss in a little bit. So once this much is done, so this indexing phase is basically mostly happening once. You don't do this again and again. This is done like one time. So if you are building a rack-based chatbot on, let's say, 100 PDF documents, you ingest it, chunk it, embed it, and store it. That is done once. And that part will be time-consuming. But then what happens on each API request to the large language model is, as user, you will be providing a query. This query will also be embedded into a vector format. That vector should live in the same embedding space as that of the vector of the chunks, because only then you can compare the vectors, right? If your query vector is living in a 50-dimensional space, if your embedded vector for chunks are living in a 100-dimensional space, you can't compare those two vectors. It's like apples to oranges comparison. So ideally, they live in the same vector space. And then you figure out what vectors in your chunk embedded space are closest in similarity to the vector corresponding to your user query. So if my query is, how much profit did Microsoft make in the year 2025? That sentence, which is user query, will be converted into one vector. Then you will have bunch of vectors which are corresponding to the chunks from the Microsoft 2025 shareholder report document. And then my query vector will be compared with the chunk vectors. And how do you compare two vectors? Like, what is one of the good ways to say, hey, this vector and this vector are similar? There are many different ways to do it. You can have cosine similarity. You can have dot product. You can simply have a distance function between two vectors. But which similarity function is used really depends on what kind of retrieval algorithm you are using. But any of them are valid. So then what you do is you retrieve, let's say, top 5 or top 10 or top 15 vectors from your database, which are closely aligned to your query vector. Then sometimes it may so happen that you have retrieved 15 items, but the meaning between this query vector, the similarity between the query vector and this vectors in this embedding space is not in the best possible way. Meaning this query vector is embedded using into a certain vector database, right? And this vector database is arranged in such a way that you need to minimize the latency, meaning you have to be able to find out the top K chunks as fast as possible. But then sometimes the top K chunks are not in the best possible order. I will show you one clear example in today's lecture when we are coding. Then what you need to do is this top 15 items which you have retrieved, you may want to re-rank, saying, actually, this is not the best similar item. This is the best similar item. So for that, you will run a re-ranking algorithm where the user query is matched with, so you will create pairs like user, let me just write it like this, user vector, comma, chunk one vector. So this will be one pair. Then another pair will be user vector, comma, chunk 2 vector. So this chunk 1, chunk 2 are the top 15 items that have been retrieved from the retrieval algorithm. And then this will be passed through another embedding model, which will be like a language model only, a large language model. But this large language model's output will not be next word prediction, because at the end of the large language model, there will be a linear layer which will project whatever the final representation is between this user vector and chunk 1 vector converted into one single token sequence. So the way it works is you will have a separator token followed by the tokenized format of chunk this user vector. Then after that sequence of tokens, you will have another separator token. And then you will have the tokens corresponding to your chunk 1 vector. And then at the end of it, you may have a CLS token or something of that sort to say that you have reached the end of sequence. And then what you do is you pass these tokens, the sequence of tokens, through this model, and then finally to a linear projection layer to produce one score. So this score will be a number like 0.58 or 0.76 or minus 0.2, which gives you an idea how similar are these two vectors. So if it is a large positive number, the similarity between them will be very high. If it's a large negative number, similarity between those two will be very low. And using these similarity scores, which you get for all the 15 pairs between your vector and the top 15 items, you can re-rank those 15 items into rank 1, rank 2, rank 3, etc. And then you can concatenate maybe the top 3 items from the ranking to produce the generated response. So to produce the generated response, you are passing two things into your large language model. One will be the user query itself. Another will be the top 3 items or top 2 items from your retrieved, re-ranked output. When you say linear projection, will we have to modify the GPT models and produce rank value? So this is not a GPT model, by the way. These are pre-trained models which are trained on producing good similarity scores. So it's like a model that already understands language, but on top of it, you would have done some fine tuning, where the fine tuning is such that you give it pairs of vectors and you give it a similarity score to predict. And when you train it on large data set like that, it will know how to predict a number corresponding to any given pair of vectors. And that number will signify how similar the given vectors are. Right. So yes, of course, you will have to fine tune the model. You won't be able to use off the shelf models like GPT. There are a couple of questions. How frequently do we have to do indexing phase? Example, my information is not constant and it will change periodically, weekly per se. Yes, very good question. In that case, if the new information that you are getting is relevant to your retrieval, you will have to do the indexing as frequently as your information changes. In many companies, however, the base document which produces the index is not that much frequently changing. In our case, for example, in our email reply agent, we will be changing so right now I have deleted the RAG database, not deleted, I mean, I have deactivated the usage of RAG database for the time being. But however, if I am continuing to use RAG, I plan to change my indexing. I plan to implement indexing once in 2 months, something like that, once in 2 months or once in a month, because in 1 month we accumulate roughly maybe 2000 email threads or something. So already I have 10,000 email threads, maybe into additional 2000 email threads add a little bit of value. So I run this indexing once in 1 month or once in 2 months, but this per request happens like 100, 200 times per day. We will discuss some more details about what type of chunking should we use. There are different types of chunkings. There are different types of embedding models. There are different algorithms for finding similarity between vectors. There are different models for performing re-ranking. Although we will be today implementing one model because we won't have time for everything, we can discuss that a little bit. So this we have already discussed. So let's discuss about a little bit about document ingestion options. So two most famous, I mean, actually three most famous document ingestion options that you may come across This you may have heard of, LangChain document loaders. Today we'll be using a LangChain document community loader. You may have heard of dockling. Dockling is very, very interesting. Recently, we had worked on a project where we built a RAG-based retrieval system for fetching documents from OpenForm library. So OpenForm is this multi-physics software library, and it's actually very difficult. So when you're performing some sort of multi-physics simulation, if you are an engineer working on something like this, it's very tricky to get solution to your problem. You will be stuck. I have worked on this back in 2015 to 2018 in different projects, and it's very difficult. Either you should have some PhD student who have worked on similar problem with you, or you should have the skill of reading the documentation or reading the wikis or reading the tutorials to understand what the solution for your problem would be. So there is a pressing need for some sort of a RAG-based chatbot or RAG-based platform which can fetch information for anybody who's working on multi-physics based in open form. So when we were working on that, one of the challenges was, okay, what chunking strategy would we use? So there we ended up finally using dockling. So dockling is really good at handling different types of documents with images as well as text as well as tables and everything, but it's a little bit slow. In fact, it is 50 times slower or 100 times slower compared to something like PyMu PDF. So PyMu PDF for very quick applications, you can use PyMu PDF for document ingestion. Document ingestion is not chunking. Okay, document ingestion is the step before that. Like the raw information which you have from PDFs, websites, or any other or TXT documents, how do you convert it into a data format which can be used for chunking, right? So PyMu PDF, if you read Reddit, you will see people praising PyMu PDF a lot. Simply search PyMu PDF versus dockling. You will literally come across hundreds of articles saying how amazingly fast PyMu PDF is and how well it works for most of their applications. But in our case, we noticed that although PyMu PDF is very fast, dockling works much better for chunking because of the complexity of our document. In industry grade RAG, you typically need OCR grade data extractors such as Mistral OCR and DeepSeek OCR. Yeah, 100%. So you can use either that or, in fact, Tesseract OCR is also very good. So implementing any of these techniques is not a difficult thing. It's a matter of importing the required library and implementing it. Then the question will come about what is the volume of your data which you are ingesting? How frequently are you changing the? Yes, this is the correct link. I think dockling.ai. Yeah, I mean, we don't go to the website that often as just importing the library, but I think it's the correct website. But what I was saying was the choice of this will come finally down to what type of document are you using, what type of data is there in your document. Is it images, is it tables, is it text, or is it a mix of those? Then whether you prefer speed of indexing that much or whether you want a mix of speed versus accuracy, right? Some of these, yeah, Tesseract OCR, in my experience also, I have used it only like a handful of times. It has not given me some output which I found very useful. In my experience, just because PyMu PDF is very fast, if you want to try something out, if you want to see how well your RAG pipeline may work downstream, PyMu PDF will give you very good start. And then if you can check how well it works, and if you want to go ahead to build a production level system, go ahead with using any maybe DeepSeek OCR or any OCR based document ingestion pipeline, or try dockling. Firecrawl, I have heard it's amazing. I myself have not used it in any project recently, or in fact any time. I think I don't remember using Firecrawl ever. Can you also show how can we modify the bounding boxes to customize OCR extraction? That will be a bit off topic, but I can figure out how to create something to answer that question. Yeah. Oftentimes we need to modify the bounding boxes for some complex PDF for 100%. So in document ingestion, for today's purpose, we'll be using this LangChain document community loader. But you could also very easily replace, I can give you a homework where you could replace that with PyMu PDF or dockling or any other. Llama index data connectors, document ingestion pipeline is good. Unstructured.io is very famous. I have seen many teams in the companies where we partnered with, they had tried unstructured.io for some of their projects. Beautiful Soup is extremely famous. Their GitHub is very, very popular. So it's often, it's very difficult for you to figure out for your project what actually works. Sometimes you have to try something out to actually get a sense of what may work for your project. In general, for complex documents, do not go with PyMu PDF or Tesseract. Just go with dockling or some OCR based techniques. Then when it comes to chunking, so this is something which many of you have asked for. Okay, wouldn't vision models of LLMs be used for ingestion? Actually, you know what? In many cases, if you are directly converting your document to tokens, right, using a vision transformer or something, it's very expensive. But OCR is a much better way. So in most of the multi-model large language model, one of the first steps is, if you give an input, one of the first things that you do is OCR, like a character recognition through opticals. You might have read the paper. Have you read the DeepSeek OCR paper? It's actually beautiful. What their conclusion is something interesting. It's like text data, if you are representing it as an image or PDF, right? You can reduce the number of tokens surprisingly by 90% or something, and still retain 95% of the information. So then it was mind blowing, because at that time when the paper came out, I think it came out some few months ago. I don't remember the exact month. But I was working on image. Then I was thinking, what is so fundamentally different about image tokens constructed using image and tokens constructed using text? One fundamental difference is that text is sort of more coarse. What I mean by that is, if you are showing the image of a cat, you cannot just verbally say cat, right? You have to show every single pixel that defines the cat. Those pixels define what is a cat. But to represent the broader idea of a cat in text, you just need the word cat. So somehow the expressive power of images and expressive power of text are completely different. And it was so surprising to me that I would not have guessed it. Like, it was so surprising to me in DeepSeek OCR paper to see that. Thanks for sharing the DeepSeek OCR paper. That even when you represent digital text using images and try to extract information out of it, you will still retain a majority of the information. I think there was the first paper. Let me just OCR. Yeah, this one, context optical compression paper. Just so this is the first paper that came in. It's came in the series of DeepSeek OCR papers. But just read this one line. Experiments show that when the number of text tokens is within 10 times that of vision tokens, that is a compression ratio less than 10, meaning vision tokens are 1/10 that of the text tokens, the models can achieve decoding OCR precision of 97%. Even at a compression ratio of 20x, the OCR accuracy still remains at about 60%. Meaning you are only having 5% of the tokens when you are representing something visually. Even if that is the case, the information retained, the amount of information that is retained in terms of accuracy score is 60%. So this is really, really mind blowing. And I think there is a lot of scope for some fundamental research in this whole area, not about DeepSeek OCR, but in general about information, the amount of information retained in optical representation of the same text versus textual digital representation. It's really fascinating. Anyways, that was a digression. So coming back to chunking strategies, there are few different chunking strategies. You yourself can imagine, if you are asked to chunk a document into different sections, if it is a huge, let's say, internet database corpus, which will have all sorts of things in it, you probably will say, okay, I don't know what all structures exist within this data because it's so vast and so huge. Maybe I'll just define fixed size chunks. So I will say each chunk is like 200 characters, something like that. But if you have a document, for example, the Microsoft document, which we will be using today, that document has sentences, that document has paragraphs, that document has subsections. So dividing it into fixed size chunks won't make sense. Why is that? In your opinion, can you mention in the chat, why do you think fixed size chunking is not a great idea always? What's the downside of it? The downside is that, let's say one paragraph number A has information related to quarter one report of Microsoft stock performance in 2025. But then let's say you are chunking it such that the fixed size is only 200 characters. Maybe then that entire paragraph will get divided into three chunks. Whereas in reality, it need not be divided into three chunks because that entire paragraph is talking about one thing, right? So basically what happened is your information, which was semantically completely related to each other within one paragraph, got divided into three different parts. So that is the downside of fixed size chunks. The good thing about fixed size chunks is it will work for complex long data, which has many different formats present in it, like internet corpus of data. And there, if you have no idea what is the perfect way to split it into chunks, you can simply go ahead with fixed length chunks. Semantic chunking is where you look at the meaning of the chunks rather than the sentence length, or whether it is ending in with a paragraph or whether it is ending in a subsection, etc. So you are creating chunks based on meaning rather than based on the structure of the language. Structure of the language will say a chunk should end with a full stop, maybe because sentences end in a full stop, paragraphs end in a full stop. But semantic chunks need not be like that. Semantic chunk can also divide your sentence in the middle, which is not a problem. Now, I have a question. If you were to implement semantic chunking, what would you need? Because how can you say that this part of the chunk is semantically carrying this meaning and another part of the chunk is carrying another type of meaning? Sure. Headings are fine. That chunking is anyway there, but you will need some sort of embedding, right? So you will create certain chunks initially. You will create embeddings, and then so what you can do is something like this. So let's say you have 4 sentences, okay? And you may do something like this. Let's say your space is a 2-dimensional space. You will say this chunk number 1, the vector corresponding to that is over here. For chunk number 2, vector corresponding to that is over here. For chunk number 3, vector corresponding to that is here. Chunk number 4, vector corresponding to that is here. Now, what do you see from this? If you say you want to do semantic chunking, which chunks can you group together to create one single chunk? 1 and 2 can be represented using one single chunk, right? Because look at the similarity of the cosine similarity of the vectors. The vector corresponding to this and this are very similar. The cosine of the angle between those vectors is close to cosine of 0, which means it's very similar chunk. So these two can be converted into one single chunk. Similarly, if you look at these two chunks, they are semantically very close to each other. And what that means is they can be grouped into one single chunk. Now you will do this repeatedly until you will either reach a maximum chunk size or you will reach a maximum chunk number in your document if that is one of your constraints. So if you say my chunk size is 500 characters, you will join different chunks which were split based on paragraphs or some other delimiters. You will convert that into one single chunk based on the cosine similarity of the vectors corresponding to that. So for semantic similarity based chunking, you will need some sort of embedding model. Then there is another chunking, which is called as sliding window chunks. So sliding window chunk can also be used in tandem with fixed size chunks or any other chunks. But basically in sliding window chunk, what you do is you will say, this is my sentence. Okay. I will define one chunk where this is my chunk number 1 and this is my chunk number 2. So the ending, some of the ending characters in chunk number 1 and some of the starting characters in chunk number 2 can be found in both chunks because there is a little bit of overlap. What is the advantage of doing this? Why is it advantageous to create chunks that have some sort of overlap between them? So what may happen is if you have chunking without overlap, there will be no, when you have overlap, some context in chunk number 1 is also present in chunk number 2. So if both chunks are related, this context will ensure some sort of continuity in the semantics or in the meaning between chunk 1 and chunk 2, right? So this sometimes these two sentences are almost saying the same thing, although when you read the words, you may not feel like they are the same continuous paragraph. But then suddenly when you have a overlapping section in between, it will help you understand that, oh, actually the second sentence is a continuation of first sentence only. So information is carried forward from chunk 1 to chunk 2 in a slightly more efficient way. But what is the disadvantage of this? Why can't I just then increase the overlap like this? I have 60% overlap or something. What happens if I do this? It simply produces a lot more chunks. So it may increase accuracy and everything, but my indexing will be super slow. The number of chunks that I have will be so high. And the most extreme case of this is 100% overlap, in which case there is no point in doing what we are doing, right? So we have to have some level of overlap, maybe 10% overlap or 20% overlap. In the example that we will do today, we'll see about the 20. We will look at the case where when we have 20% overlap, meaning 500 characters per chunk and 100 character overlap. Then there are even simpler chunking strategies like sentence-based chunking. Sentence-based chunking is you literally look at where the period is coming. So it need not be like one chunk equal to one sentence. It can also be like one chunk equal to two sentences. But chunk boundary will always come in between sentences, wherever the period is coming, right? And the most interesting way of chunking, which we will be doing today, is called recursive chunking. So recursive chunking, what it does is, if you have a big document, all right, this big document can be split into sections. It can be split into paragraphs. It can be split into sentences. It can be split into words. And then you will decide, depending on the size of the chunk, whether an entire section will be one chunk, or an entire paragraph will be one chunk, or a few sentences will be one chunk. So let's say your chunk size, maximum chunk size is 500 characters. Let's say you may have a Microsoft financial document with one subsection 1.1, which is just one small paragraph like this. But then you may have a subsection 1.2, which may have two big paragraphs. And let's say this paragraph is 500 characters. This is 500. This is 500. So in this kind of chunking, this whole subsection is chunk number 1. But then the subsection 1.2 is actually not one single chunk. It's actually divided into two chunks. So depending on the length of each sections, the one entire section may be found in one chunk. One entire paragraph may be found in one chunk. Maybe just 2 or 3 sentences may be found in one chunk. It depends on your page structure. So today we will see how this recursive chunking output will look like after we do the chunking. Okay. Then this we have already discussed, data converted to vector. So one thing I want to reiterate is your chunks are converted to vectors. So these are all different chunks. But then into that same vector space, you also need to convert your query. That's when you can compare cosine similarity or dot product or any other similarity metric, L2 similarity between this vector and your chunks. Okay, so that is one thing you should remember. So whatever embedding model is used for producing vector representation of chunks, same embedding model will be used for vector representation production for query. And for embeddings, there are again many different options. These are all language models which can produce very good semantic representation of languages in the form of vectors. So just let me ask you a question. What is the primary difference between BERT model and GPT? Like, is BERT a language generation model or is it something else? So the main difference is that BERT is a very good model for understanding language, because BERT is not trained on next language prediction. BERT is basically trained on masked language modeling. So if you have a sentence like the cat sat on the mat, you will produce mask tokens in between. The mask sat on the mask. And the BERT model is trained in such a way that this mask token, whatever the token associated with this mask token, that is what the model is by default taught to predict, right? And because of this, BERT as a model, it's really, really good for encoding the language. So similarly, here what you actually need is, you don't want a model which is like ChatGPT. You want a good representation of the model in vector space, which can capture the meaning in the language. And where is the language coming here? The language is coming in chunks. So you want a good vector representation of those chunks, which are languages, in an embedding space, which means you can use any good language model for this task, but there are specified specialist models like sentence transformers or OpenAI embedding. So this will not look like exactly like GPT. It won't be performing next prediction, but it would rather be performing embedding. So language will be just converted to vector. There is no agenda of producing the next token. So in today's, and there are many, there are Mistral embeddings, there is Hugging Face embeddings. I have used at least 5 of these in the last several projects, but today we'll be mostly using sentence transformer. It's very simple to use. This mostly this exact same model we can use, all mini language model. L6 means 6 layers. V2 means simply the second version of that model. So this we will use in today's project. And this I have already talked about, so I will not be spending more time on that. Oh yeah. So how do you select the dimensionality of your embedding space? Let's say you have one embedding space with 64 dimensions and another embedding space with 728 dimensions. What is the trade-off here? If your embedding space is small versus big, what is the trade-off? Big embedding space has more expressive power. If you have 728 dimensions to express a chunk, it means you are having more options, right? So more variety can be captured. In 64 dimensional space, you can only capture that many dimensional information. But the problem is again latency. So to perform similarity search in larger dimensional space could be difficult because there are a lot more options. If it's a 2-dimensional space, it's very easy. 1-dimensional space, very easy. If it is a 728-dimensional space, it's the difficulty increases. But then, so it's a trade-off between what may work for you for your specific case. It may depend on number of chunks that you have. It may depend on how fast you want the retrieval to happen, etc. Plus how good your chunking accuracy should be. If your entire PDF document is talking mainly about one idea, okay, would you rather go with a 64-dimensional chunking or 728-dimensional chunking? So I will rephrase my question. Let's say you have one huge PDF document, okay, and in RAG, you want to use this document to retrieve relevant sections from it. So that goal is unchanged. But this whole document is about, let's say, mostly one idea. Let's say cook a recipe of one single dish or something like that. So what may happen is the diversity of the information present in your document may not be that high. So if diversity is not very high, if you use a lower dimensional space, the vectors in the lower dimensional space may be very close to each other, which means the whole idea of chunking itself will be useless. Because why do you even create chunks in the first place? You want to create some distinctions between this section and that section and next section, right? So if your document has very little diversity, but you still want to produce chunks that are meaningfully separate from each other, you may want to use higher number of dimensions. But if your document already has a lot of diversity, right? It is like if it has many different words, let's say one part of the document is talking about quantum physics, another part is talking about cooking, another part is talking about some other thing, then already the chunks are very diverse. So when you use an embedding model which is not as powerful also, the inherent diversity in the input data itself will take care of the fact that you want to separate your chunks a little bit. So in that case, you can go with 64 dimensional chunking also. 64 is just an example, by the way, but you can go with lower dimensional chunks. So to capture nuances, you will need more dimensions. But if the differences are already inherently present in the data, you can go with lower dimensions. Then similarity search, there are actually many different ways in which the similarity between two vectors can be defined. These are probably the three most popular ones, but some of the complex vector similarity search algorithms use even similarity search like approximate nearest neighbor, etc. So I don't want to go into the details of this because that will simply prolong the lecture by a lot. But just understand that these are indices using which you can say which vectors are close to each other. Cosine similarity is just the cosine of angle. Dot product will also take magnitude into account. Euclidean distance is like square of the distances between the vectors. And now comes the most important thing, vector indexing, or how the database look like. You may have heard of most of these. FAISS is Facebook AI Similarity Search. This is extremely fast. ChromaDB is very popular. I had shared one document from Chroma day before yesterday about, I think it was about context rot. And Pinecone provides cloud vector storage. ChromaDB can run locally. It's very fast, but it's apparently not that accurate, but it's very fast. So here what it does is, can anyone tell me what's the difference between vector index or this vector database versus similarity search options versus the kind of embedding model that I use? What is the difference between those three things? Embedding model versus similarity search versus vector index. Let me ask you, what's the difference between these two? Similarity search versus vector index. Isn't similarity search already performing this the search between identical vectors, basically between your query vector and your vectors in the database? The basic idea is that this vector index, right, the different vector index provided by different libraries, will be using one of the or multiple of the similarity search algorithms. So these are actually algorithms. Cosine similarity is an algorithm, is one way to define similarity. Dot product is one way to define similarity. Now, these algorithms, for example, Facebook AI search algorithm might use this IVF, inverted file index, or it may also use ANN. I don't think it is mentioned here, but FAISS, in my understanding, it also uses approximate nearest neighbor. So it can use one or multiple of similarity indices to produce the similarity score between your query and the vectors already present in the database. The embedding model simply produces the vector. So this produces the vector. Similarity algorithm tells if you have two vectors, what is the similarity score? Vector index makes finding of the score between your query, and let's say there are 10,000 vectors in your index. How are you going to search for the closest vector corresponding to your query? Are you going to search one by one? Are you going to say, hey, let me pick the first vector from my store and I will compare it with my query. Then I'll pick second vector and compare it with query. Third and compare it with query. Then you will have to run it on the order of 10,000 times, which is very inefficient. So vector index makes this score finding very efficient. So in one of the projects that we did 2 years back, it was about, so there was a company, basically they wanted to build something for their client. Clients are like diamond merchants or jewelers or something like that. So if a customer comes saying, hey, here is a piece of jewelry, I want something very similar to this. That is what I'm looking for. And in their inventory, the store will have a lot of different jewelry items. So it's very difficult for them to know whether something similar to what this customer is looking for exists in their inventory or not. And there we implemented similarity search. So we embedded the images as vectors and we did a vector search, similarity search. And there we could see that the difference between Facebook AI similarity search and a vanilla AI similarity search was day and night. It was huge. So this FAISS is very, very good. And in fact, today we'll be using Facebook AI similarity search. There are many other different ones. You may end up using any of this depending on your application. I can't say the details, unfortunately, of the company. Then there is one more question that you may have is what is LangChain and what is Llama Index? Basically, LangChain and Llama Index are basically overall frameworks which will allow you to implement all the things in the pipeline. It will allow you to implement document ingestion. It will allow you to implement chunking. It will allow you to implement any kind of vector database or many kinds of vector database. It will allow you to implement similarity search using indices. And then when you after basically the very last stage until retrieval happens, LangChain or Llama Index can take care of. Which one do I recommend? I actually honestly don't have a preference. I have used both, so I really can't say which one do I prefer. So I will show you. There is one image which I wanted to show you. I don't know if I can find it. Uh, I don't have it handy, but I will share it with you separately. Basically, these frameworks will allow you to stitch together different components. So RAG is a collection of different components, and this framework will allow you to stitch them very easily. LangChain is literally, it's a chain of, if you want to build AI agents or if you want to build AI frameworks, there are many different providers. There are providers for database. There are providers for chunking. There are different libraries for performing document ingestion. So LangChain, for example, will allow you to chain together different parts of that to produce one single pipeline. You can do without that also, but it makes it easy. Now let's discuss the one last idea before we will start coding, which is TF-IDF. So TF-IDF stands for term frequency inverse document frequency. So I'll tell you why this is useful. In many cases, before this modern natural language processing became very popular, the traditional NLP handled sentences in terms of words. So you could also create vector database for sentences. How can you do that? For example, let's say this is my whole vocabulary. The words are cats, drink milk, dogs, water, eat fish, right? So only like 6 or 7 different words are present in my entire vocabulary. So I can define like a 7-dimensional space. I can't draw it fully, but I can define a 7-dimensional space. And then I can say cats drink milk is something like first dimension is there, second dimension is not there. So if there are 7 dimensions and the word cats is the first dimension, word drink is the 5th dimension, word milk is the 7th dimension, those dimensions will have values, but rest of the dimensions will have 0 values. So it's called a sparse representation. The typical vector representation that we discussed so far is called dense representation. Dense because along most of the dimensions, there will be some value. But in sparse representation, most of them will be zeros. Along some dimensions, there will be finite values. Then what we can do is, this is a solid example of how TF-IDF works to create re-ranking. Let's say you have 3 documents, okay? Or 3 chunks. Cats drink milk is one of them. Dogs drink water is another. Cats eat fish is the third. And your query is cats drink. Now, if we want to say, corresponding to this query, whether document 1 is the most similar or document 2 is the most similar or document 3 or 2 or 1, whichever is the most similar, we want to do that based on TF-IDF score. So let's see how to do that. So cats drink is our query, and there are 3 documents, n equal to 3. So first thing is calculating something called as inverse document frequency. So inverse document frequency is higher if the frequency with which a word appears in all the documents are low. Meaning, if a word is very unique to one particular document, it's a very valuable word, right? So IDF formula is logarithm of total number of documents divided by number of documents in which this particular word is appearing. So can you tell me what would be the formula for inverse document frequency for the word cats? So you have 2 words in the query. One is cats and one is drink. So cats IDF will be what? IDF for cats equal to log of n. N is 3 because there are 3 documents divided by cats is appearing in 2 documents, right? Document 1 and 3. It will be something like log of 3 by 2. Similarly, IDF for drink will be log of number of document is 3 divided by drink is appearing in 1 and 2. So again 2, same. So the IDF should be ideally same for both. So logarithm of 3 by 2, 0.405, logarithm of 3 by 2 for 0.405. So inverse document frequency is the same. This is not very useful as individual metric, which is the reason why we also introduced a term called term frequency. But inverse document frequency has one interesting thing. Just tell me this. If I have a word, let's say I have a book on some sort of children's story. Okay, so this is like a kid's story book, and I have some query, and I want to find the answer for this query from this book. Now, let's say I have in one of the queries, query number 1, and another query number 2. In this query number 1, one of the terms is quantum. In query number 2, one of the terms is, let's say, cat. Now, can you tell me in which of these cases, so this will be divided into chunks, by the way, in which of these cases inverse document frequency will be higher? In query 1 or query 2? This is query 2. When will IDF be higher? Is it for cat or is it for quantum? Let's think about it logically. Okay. If the user's query contains words like cat, how easy or difficult it is to find the relevant section from kid story, if it exists. So the assumption here is that if the user is asking a query, something about this exists in the kid story. So something about quantum exists in the kid story, something about cat also exists in the kid story. This is a big book. But then the frequency with which quantum may appear in a kid story book would be very rare, right? So the inverse document frequency for the word quantum will be a very high number because n, let's say the n is equal to 150, and quantum may be appearing in 1 or 2 places. It's not something which appears very frequently. So then it will be logarithm of 150 by 2, which is a very high number for query 1. Whereas inverse document frequency for cat might appear like 100 times, who knows? Then that will be a small number, logarithm of 150 by 100. So the rarity of the word in the query is one good thing you can leverage to find the appropriate section which you are trying to query. So if the word in your query is so rare, it's actually very useful for you. But then sometimes non-rare words are also useful. What if the user is actually asking something about cat? User is asking something about something related to cat, and there is one chunk here which contains reference to cat 10 times, right? So the frequency with which the term cat is appearing in chunks, yes, here each chunk you can consider to be separate document, correct? Kid story is not the document. Each chunk is a document in this case. And we are trying to find corresponding to the query that we ask, which chunk is the most relevant chunk, okay? But in the words of TF-IDF, which document is the most relevant document? So if in one of these documents or one of the chunks, if the word cat is appearing 10 times, that also has value because query 2, yes, the cat has very poor inverse document frequency, but the frequency with which the word cat is appearing in this chunk is very high. So that is the reason why one more term called TF or term frequency is introduced. So term frequency is the following. Let me copy paste this over here. So term frequency is, in your query, you have 2 terms, cats, drink. Those are the 2 terms. So cats and drink. How many times does cats appear in document number 1? Only once. So this is the cats. So cats appear once in document number 1. Drink appear once in document number 1. This is drink. In document number 2, cats does not appear. So it is 0. Term frequency for cats in document 2 is 0. But term frequency for drink in document 2 is 1. And document 3, for that, cats appears once. So that is 1. Drink appears 0 times. Now that in TF-IDF is basically the product of TF, term frequency, multiplied by inverse document frequency. So for document 1, for the term cats, TF-IDF will be 1 multiplied by logarithm of 3 by 2, which is 0.405. That is 0.405. For drink also, it will be the same. So for document 1, the total score of TF-IDF will be 0.81. But for document 2 and document 3, the score will be 0.405 and 0.405. And you can see that logically also, you don't even need TF-IDF here. If you simply look at your query cats drink, just visually, it is most similar to this one, right? It is not most similar to this or this. You can already see that because here cats drink is already present. So this TF-IDF is also telling the same story because now the score is like 0.81, 0.405, 0.405. So after re-ranking, the order in which your documents will be arranged will be document 1 will appear first and document 2 and 3 will appear next. Similarly, and that's the reason why we are multiplying with the TF, because if we gave all the weightage to IDF, here in this example, if somebody asked from this kid story chunks, if the query had something to do actually do with cats, it should not be penalized just because the IDF score of the cat is very bad because cat is appearing 100 times in 500 chunks. But there is one particular chunk in which cat may be appearing 10 times or 50 times. And that chunk may have very high similarity to this query. And how do we capture the fact that 50 times cat is appearing here? In the form of TF, term frequency. The term frequency of cat in document number, let's say this is document number 11 or chunk number 11. In chunk number 11 will be equal to 50. IDF of cat in the whole document will be equal to logarithm of 1.5. And this will be a relatively small number. So the total score of the cat, considering this query and all these documents, will be 50 multiplied by logarithm of 1.5. So that will be a number which is probably not that small. Now, similarly, let's discuss quantum. Quantum has very high IDF, but its term frequency will be very small because quantum as a term will be appearing in only very few chunks, right? So only very few chunks will have term frequency, a high term frequency for quantum. For most of the chunks, quantum will have very low term frequency. So that's why term frequency and IDF creates a balance between a rarity and more commonly occurring words. Yes, exactly. So this is a very different type of embedding. We are not going to implement this, but I just wanted you to be aware of this. This is not a this also you can call as a vector embedding, but it's not a dense vector. It is a sparse vector. Why? Because here the vectors can themselves be, each dimension of the vector will be one word. So if your vocabulary has 10,000 words, each dimension will be one word. So every word in your query will be represented using one vector in a 10,000 dimensional space. But it will be a sparse vector. It will be a sparse space. Why is it sparse? Because most of the dimensions will be absent. Because the word, this sentence, for example, let's say I have 10,000 words in my vocabulary and the query is cats drink. Along one of the dimensions, along cats, I'll have a value of 1 or something. Along another dimension for drink, I will have a value of 1. But for all the other 9,998 dimensions, the value will be 0. So this will be a very sparse space. I just wanted you to be aware of this because in RAG, sometimes you use both approaches or a mix of both. Sometimes you use dense search. Sometimes you use sparse search. Sometimes you use hybrid search. So just be aware of its existence. Now, I think it's a good time where we can go ahead and implement RAG. One small thing is in your context window, typically 60% up to 60% can be reserved for output which you get after RAG, right? The of the entire context window. This is a poorly constructed context window, by the way, in my opinion. 10% generation buffer, even Cloud Code throws a warning after I think 80% or 86% of your context window is filled. Okay, so now can all of you open Google Colab notebook, an empty Google Colab notebook? Let us start coding from scratch the RAG chatbot. All right. And one thing you will need is either an OpenAI API key or you will need a Gemini API key. Other API keys are also fine, but the code, you will have to modify the code a little bit, which can be easily done using Gemini, not a problem. But I'm just saying, just in case. And API key is the best way for you to store API key in Google Colab is here. Press this key icon. You can add new secret and all the secrets will be over here. And this will be stored almost permanently in the sense that even after you close the session or even if you open a new Google Colab notebook, these things will be available. So all you need to do is like, you just need to enable it. So this makes your life much easier instead of storing it in temporarily and then having to copy and paste it again and again. This will store that hassle for you. So now we have to start this in a few steps. So first step is importing the required libraries. All right. Then after that, we have to write the code for uploading the document so that Google Colab can access it. Then third is we can have the document ingestion pipeline. If any of you want to follow the exact code that I'm writing, you can just use this link. Just take a copy of this if you want to use the exact code. So the libraries that we will need is, so we'll have to, before importing, actually, we have to install certain pip install. So pip install sentence transformers. This is for embedding. I can write it in one line, sentence transformers, then Facebook AI similarity search, which can run on CPU, FAISS CPU, LangChain. Then if you don't want to write everything in one line, just write again pip install PyPDF. So I'm not using PyMu-PDF here. I'm using PyPDF. Anything works, does not matter. And then LangChain community. Then pip install LangChain text splitters. You will see when we come to the part where chunking and all are implemented, where these things are used. So just add these things and run it to install those libraries. Just name this as RAG chatbot from scratch. I had already installed this. That's the reason why it says requirement already satisfied. All right. So this should not take you more than like few seconds. It's very fast. So once this is done, we can write the code for uploading the document. So uploading meaning it's a PDF document. So from google.colab, import files, then uploaded equal to files.upload. So we are using this files.upload function. And then for file name in uploaded.keys, because you could also technically upload multiple documents, but uploaded.keys will fetch the file name corresponding to whichever document you upload. You will see that in a moment how it works. Print uploaded. This is just to see if whether the upload has finished successfully or not, comma, file name. So now when you run this, it will ask you to click and upload. So here it is asking to choose a file. I can choose it from my desktop, but in case you want to have access to the same file which I'm going to use, you can search Microsoft shareholder report 2025. And I think it is this page only. Yeah, go to this page and do Control P. If you do Control P and save as PDF, this whole thing will be saved as, I think, when I saved it, it was 98 pages. Here, I don't know why it is showing 67 pages, but doesn't matter. So I'll share this link with you. Just go to this page, do Control P for printing, and it will save this annual 2025 annual report from Microsoft. So I already have downloaded it on my desktop. So I'll just go to my desktop and Microsoft. Okay, so uploading is done. The last sentence, uploaded Microsoft 2025 annual report .pdf. How to download? Just do Control P. Control P is the print command after going to the website, and it will ask you option to print and then save as PDF. Just save it as a PDF in your local. Otherwise, if this is not a very big document, I can also try to share it here in the chat. I don't know. Oh, it's 1.8 MB. I'm directly sharing it in the chat here, so you can download it from the chat. All right. So when you run this, it will ask you for choose files. The button will be there. Just click it and upload. Now the next part, from LangChain _ community dot document loaders _ loaders import pi with capital P. So upload option you will get only when you run this block of code from google.colab import files. Only when you run that, you will get the upload option. Import pi PDF loader. And this is actually not loader, this is loaders. And then PDF _ file equal to list of uploaded dot keys. So uploaded dot keys was also referenced here, which will be the name of the PDF document which we uploaded. Of 0 means you are referring to the 0th document which you have uploaded, which is this Microsoft annual report. You could upload multiple documents also. Then loader, this is where the ingestion is coming into picture. So instead of PyMu PDF, we are using PyPDF. PyPDF loader of PDF _ file, which is this name, PDF _ file. And then documents equal to loader.load. So this is just a function that we have to call from this loader object, and print number of pages loaded, and this is equal to length of the document. So this PyPDF loader basically creates it such that it recognizes page 1, page 2, page 3 separately. So len of documents will tell you what is the total number of pages. Okay, so if I just run this, you will see whatever that number of pages in the PDF is. And this part may take a little bit of time. It's not as slow as chunking or anything. It's just document ingestion, but this may take a few seconds. Has anyone reached till here? Is everyone on track? Did you upload the document? Okay, awesome. Okay, so print number of pages loaded is 98. So there are total 98 pages in the PDF. I thought it was 68. I don't know why here it's showing 98. Maybe I downloaded a different document or something. Anyways, doesn't matter whether it's the same document or different document. Not able to import LangChain community loaders. Is there any spelling mistake? Or did you install this pip install LangChain community? This you will have to do it. All right. Then we can just print one more thing. Print documents of 0. Can you tell me what is this? What is documents of 0? Len of documents is the length of pages, which means documents of 0 is the content in the first page, basically. And first page you can actually see here. Let me open the file. It has not opened yet, but basically the first page is this. It's not here. When I printed it, it was this. You see, it's like a table of content. So whatever is there in this first page is getting printed when I say print documents of 0. If I say print documents of 3, whatever is there in third page will get printed, and that are these paragraphs. Okay. So it's just to see whether whatever we have loaded is the same thing as what we intended to load. Now, what is the next step after ingestion? Chunking. Yeah, so the required dependencies are these. For installation, these are the ones. And after you install, these are the imports. Only one thing you need to import. From LangChain community, document loaders, .document loaders, import PyPDF loader. Okay, so document has been loaded perfectly. Everything is good. Now let's perform chunking. So for chunking, you have to use from LangChain _text_ splitters import. So here we use recursive splitter. So recursive character text splitter. So, and then text_splitter equal to recursive character splitter of. And then here we have to define chunk size. So let's say chunk_size is equal to 500 and chunk underscore overlap. So overlap between individual chunks is let's say 100. So here 500 is the number of characters per chunk. 100 is the number of characters that are common between first chunk and the next chunk. So which means 20% overlap will be there between two chunks. Then chunks, this is where chunks are defined, is equal to, just copy this text_splitter dot split underscore documents, which is the function. And here we have to pass the documents that we defined here, which is the variable documents itself. So this documents we have to pass, which are documents defined in pages. Now the chunking is done. Now, if we want to see whether the chunking has happened or properly or not, print total chunks created, and that will be length of simply chunks, because number of chunks is length of chunk, this variable chunks. So if we run this much itself, we can see whether chunking has worked effectively or not. We can print a sample chunk a bit later once this is done. So total chunks created 583. Okay, so chunking is successful. And then print, this is just to display one of the chunks. So from the 0th chunk, so chunks of 0, this will be one particular chunk. We want to display the content of it. So page content, we don't want to limit it. We can display the entire page content. So if we run this, see, so 0th chunk, from the 0th chunk, we are displaying all the content. So this is the 0th chunk. Okay. From LangChain text splitters, import number of chunks is 706. Okay. Are you using chunk size 500 and overlap 100 or different? I don't know if we are all using the same document or not. Ideally, there should be no difference because everything else is the same. Okay, so I think people who is using 67 pages, it's a different document. Mine is 98 pages. Okay, so I want to show you one thing. Okay, so here this is the 0th chunk. Then let me also print chunk number 1. So look at the last, in the first chunk, in the 0th chunk, look at the last few items. Investments, derivatives. This is from the page 1. Okay, in my page 1, it's like the table of content, investment, derivatives, these things. Those same things are being repeated here. You see, investment, derivatives. Why is that? Why do you see the same thing here and here? Because of the exactly sliding window. We have defined a 100-character overlap. If overlap was 0, the second chunk will start exactly where the first chunk ended, right? So chunking is working perfectly. This is what it means. So now we can generate embeddings from the chunks. So import Facebook AI similarity search, import numpy as np. Then from sentence underscore transformers, import sentence transformer. So this is where we convert the chunk into embedding using sentence transformer, a very specific model. Then we say embeddings. Before embeddings, we can define the model equal to sentence transformer of. So just copy this. We have to pass the name. The name is all mini. Number of layers is 6 and v2 version 2. So this has, I think, around 300, no, 22 million parameters. This is not a very big model. Compared to small language models, this is even smaller than that, because even SLM, small language models themselves, have 1 billion parameters. This is only 22 million parameter model, roughly. Then using this embedding model, we can create embeddings. So embeddings is equal to model.encode. So using the sentence transformer, we are encoding. And what are we encoding? We are encoding the chunks. So chunk dot page underscore content. And this we have to do recursively for every chunks. So for chunk in chunks. So for each chunk in the chunks, so chunks variable is defined over here. We are recursively converting the content of each chunk, which is chunk dot page content, into encoding using the model all mini L6v2. It's a sentence transformer. Then we can say dimension equal to embeddings dot shape of 1. So this will just store the dimensions of this model here so that we can print it and see it. Then we need index. Index is equal to Facebook AI search, Facebook AI similarity search dot index flat L2. So flat L2 we had defined, it is the L2 difference between two vectors. It's neither cosine similarity nor dot product. It's the fourth item which we had discussed in the, it's the square of the distance between two vectors. L2 of dimension, because we have to pass how many dimensional space are we looking at to calculate the distance between vectors. And then index dot add np dot array of embeddings. And print. Now we can just say, I want to have a look at how this looks like. So total vectors in the index equal to index dot n total. This is the total number of vectors. So when we print this, can anyone tell me what should be the output of this statement? When I run this, what is the number that we are going to get? It should be same as the number of chunks, because each chunk is getting converted to a vector. So mine is 583 or something. Yours should be 700-ish if you're using the other 67-page document. This embedding also may take like 1 second. Oh, one more thing is you may need a Hugging Face token. So I have it stored here. So you will have to get a Hugging Face access token from Hugging Face, but I'm just clicking grant access. There is some issue here. Local and not valid model identifier. This is a private repository. Make sure to pass a token. Sure, we can pass the token. Mini LM. Yes. Thank you so much. So my Hugging Face token is also stored here, HF token. And you see, when I grant access, automatically this is ticked. Or if I already tick it, it will not ask me to grant access. Access is already granted. So this is just verbose that are getting printed while we are importing FAISS and creating the index, but this may take a minute to finish. Okay, that is done. And see, total vectors in the index is 583. Okay, so that is also perfectly working. Now, an interesting thing we can do is we just want to see how our chunks look like in our embedding space. It's a how many dimensions were there? I should just print this. So print dimension. I think it's 384 or something. Yeah, so it's a 384 dimensional space. What if I want to just visualize how one vector looks like? It can be easily done. So import matplotlib dot pyplot as plt, and then numpy I think I have already imported. Define visualize embedding, and here we will pass a vector to visualize. We will pass a corresponding chunk text equal to, by default we are not passing, then max text characters is equal to 500. Sentence embedding will be downloaded and hosted in collab, and will context and will remain available. Correct. Remain available in the current session. If you quit the session, I think it will be gone. I don't know if it is stored in the temporary storage or between session. I don't think it carry forwards between one session. If you and terminate the session, I think your the downloaded sentence embedding is gone, if I'm not wrong. Okay, so define just visualize embedding. We are passing the vector chunk and the size, max size. Then vector equal to np dot array of vector, this vector. Then normalized vector, we are just normalizing it before visualizing. Normalized equal to vector minus vector dot min to find the minimum value inside the vector. Then divided by vector dot max minus vector dot min. I can just copy paste this. So normalizing it such that the range of values are between 0 and 1. Then color band, just to define the colors of my visualization, equal to normalized dot reshape 1 comma minus 1. You will see the output when I print this. And then if chunk underscore text is not none, then print chunk text and the next character slash n, then print chunk underscore text and print the first 500 characters, max text characters, and just print. And then matplotlib plt dot figure of fig size equal to 12 comma 2. So it will be like a row. It will be a very long figure horizontally. Then plt dot im show of color band comma aspect equal to auto and color map equal to viridis. This is very standard in all vector visualization. I have used this in many times. The tick marks on y-axis, y ticks, plt dot x label, just to see what the chunk is. Embedding dimensions. This is just to display the embedding dimension, but we don't need it. We already know that it is 384. Len of vector, and then plt dot title of vector representation. This whole function I can actually share with you. You don't necessarily have to write it. Plt dot show. So this is just the function. I don't think there is an issue. I hope it works. So this is the function just to do our visualization. And if you want to visualize one of the random vectors from our chunks, the embedded chunks, just call the function. The function name is visualize embedding. And into this, we passed one of the embeddings. So embeddings of, let's say, 1. And then we also pass the corresponding chunk. So we say chunks of 1 dot page content. Then if we run this, hopefully we should get the visualization. There is some issue. Embeddings of one. Let us ask Gemini. Okay, where this? It's very dis. That's why. All right. So this is the vector. So basically, it's a 384 dimensional vector. Each color corresponds to the magnitude of that particular dimension, right? So each there is like a strip. So if this was like just 3 dimensions, you will just see 3 colors. But here you are seeing 384 colors. But this color band is literally how this whole thing is represented. And if you want to see how some other chunk looks, let's say chunk number 5. So embedding number 5 and chunk number 5 you pass, you call the function. Now this is the chunk. Chunk is something about quarters approaching each day. So basically this whole sort of like three-line paragraph is represented using this one vector. So this color map visualization is so useful to see how the uh, sentence transformer has converted your input into just pure numbers. All right. It's just for visualization purpose, no other purpose. Now retrieval of the chunks. So query equal to input of enter your question. So this is where the user will ask the question based on the document. Then we need to convert the query to an embedding. So query embedding. And for this, we will use the exact same model that we defined up here. So here we have defined the model equal to sentence transformer. So copy that same thing equal to model of model dot encode of query. Then if you want to visualize how your query looks like, your query will look like visualize underscore embedding of query underscore embedding. So you pass the query embedding and the query itself. If you do this, you can just see how your query has become a vector. So let's say my query is how much profit did Microsoft make in 2025 compared to 2024. So let's say this is my question. That whole query will be converted to vector using my embedding model. So this is now how my question looks like. So now what is the goal of RAG? The goal of RAG is to see this color band is matching with which color band. So there are a lot of chunks, 583 color bands corresponding to chunks. Basically, it's like comparing these two vectors. Now, d comma I index dot search. So index is the Facebook AI semantic search, the variable for that. Index dot search np dot array of query underscore embedding. And you are looking for top 5 similar items. Then retrieved chunks. Yes, we will also apply reranking here. Very good question. Yes, we will. Chunks of I for I in I of 0. Then we can just print it. Print top retrieved chunks. And then I can print the retrieved chunks in the next line. So /n for chunk in retrieved chunks. So we are recursively through a loop going through these retrieved chunks. Print chunk dot page underscore content. And then we say print. We also want to see these top 5 chunks that are closest to our thing, they are coming from which page? Because that is very important for us to know. Where does this chunk come from? Meaning, where is the reference to this particular retrieval? Then we can say page chunk dot metadata. And from the metadata, I want the page number as the metadata. And then I can just print, because we are displaying 5 chunks, I can just put some stars or something in between the 5 chunks, in between each chunk, and just run this. So now these are my retrieved chunks. I can just replace this with something else. So these are my retrieved chunks, okay? So top 5 chunks, this is the first chunk. And you can already see that my question was, what was the profit in 2025 compared to 2024? And you can see 2025, then 2024, 2023, etc. This is the first chunk, and this chunk is coming from 9th page. There is another chunk coming from 23rd page, another chunk coming from 87th page, and then 2 more chunks. So totally 5 chunks. These are the top 5 chunks corresponding to my query. Then we need to perform re-ranking, because what if this is not the order in which the chunks are most appropriate to my query? Then we say, there is a question from Sandeep. Can re-ranking happen within the retrieved search itself and retrieve based on highest similarity search? The re-ranking model is actually, think about it. In re-ranking, you are comparing every query with the chunk. Now imagine you have to do that for all the 10,000 chunks. It's very time consuming. So re-ranking you do separately only for the 5 chunks. If you want to do it along with the retrieval, it makes the process very slow, because you will be retrieving while also looking for similarity search. I mean, not retrieving, I meant to say re-ranking. You will be re-ranking while looking for similarity search. So you don't do re-ranking while doing that. You first find the top 5 similar things, and then you re-rank using a either similar sentence embedding model, or an even more powerful one. And by the way, sentence embedding model for re-ranking is not producing vector or anything. It's producing a score. It's producing a score like a 0.5 or minus 0.6, etc. You will see that in a moment. So here, from sentence transformers, import cross encoder. Cross encoder, because you have 2 sequences here. You have sequence corresponding to query and sequence corresponding to the chunk, the 5 chunks. Re-ranker equal to cross encoder of cross encoder / ms Marco mini language model L6 v2. And then the pairs that we are passing into the re-ranker are query, comma, chunk page content. So chunk dot page underscore content. For chunk in retrieved chunks. And I think there is a, yeah, I think this is correct. Then scores is equal to re-ranker dot predict of pairs. So basically re-ranker will predict between the query, comma, chunk pairs. There will be 5 such pairs. What is the score for each of the pair? And then ranked chunks equal to, you just sort it based on decreasing order of score. Scores, comma, retrieved chunks. And then lambda reverse equal to true. So highest one should come at the top, lowest should come at the bottom. And then print after re-ranking, we just want to display the order in which chunks are appearing. For score comma chunk in re-rank chunks. Print score comma score. So this will print the score corresponding to the top chunk, and we will do that. Also, do we get any difference in output when we use different embedding model for query and our knowledge base? We can't use different embedding model, right? Because the embedding models will be completely living in different spaces. So we have to use same embedding model. Then score is printed. Then let's print the chunk dot page content. Then what else do we need to print? Print page number, also print chunk dot metadata of page. So page number is chunk dot metadata of page. And then to just separate between the different chunks, I can just print like a dot dot dot. All right, so now let us run and see. So one thing, the way to see if the re-ranking has changed the order is look at the order in which my initial chunks are appearing. 9, page number 9, 23, 87, 29, 29. I'll just write it somewhere. 9, 23, 87, 29, 29. This was the order in which it was originally appearing before chunking, before re-ranking. So after re-ranking, let's see if something different happens. So yeah, so after re-ranking, see 29th page chunk in the 29th page has come to the top. So after re-ranking, the order has become 29, 87 pages a second, 23, 29, 9. So the order is literally 29, 87, 23, 29, 9, I think. So this is after re-ranking. So before re-ranking, the chunks were appearing such that one of the chunks from page 9 was at the top. But then you look at what has happened after re-ranking. I think the 9th one has went to the last. And let's see why that happened also. And look at the score. Score is 0.488158 what was my question? My question was, compared to 2025, how much has the revenue changed compared to 2024? So here it says, in this chunk, look at what it says. An increase in office transactional purchasing with the launch of Office 2024. Consumer product and cloud services revenue increased $760.56 million. Microsoft 365 revenue grew 11%. Consumer subscriber growth of 8%. So look at this. This has the actual information which I asked, right? The last one does it have the information? Microsoft Corporation. I think this is the stock price of Microsoft, probably not it's the share price. I don't think it's the revenue or anything in this last one. Maybe I'm wrong. I don't know what this 100, 140 means. It's probably the share price. But so the re-ranking has actually helped us to find out the most relevant chunk to the top. Now what we need to do is there a chance the most similar chunk to the user query is not from the top 5 chunks? It is possible, which is why you have to sometimes increase the top 5. Instead of top 5, do top 15. But then the problem is sometimes you will have a lot of chunks that are also useless. Then you will have to remove some of them after re-ranking, right? Now let's append combine the re-ranked chunk with the context. So combine re-ranked chunk with context. So top underscore chunks equal to chunk dot page for underscore. So first, whatever is returned first does not matter, comma chunk in ranked underscore chunks of 3. So only top 3 we are picking. From the re-rank chunks, the top 3 we are picking. Remaining 2 are being discarded. Then context is equal to /n /n dot join. So just adding a next line character at the top, then join top chunks. So these chunks are joined. Then print context. So we can just see when we join the top chunks, how the total context looks like. Just run this. So now this is how the total context looks like now with the top 3 chunks after re-ranking is combined into one single sequence of tokens. Now the last step is generate answer using LLM. And this is where you might need OpenAI or one of the APIs, Gemini or OpenAI. So here import, I'm using OpenAI. Then from google.colab, import user data. Then prompt is equal to we don't need to give this, but I'll just write this. Answer the question using the context below. So this is the system prompt which we are giving to the LLM. Then context is the context which we just created using the chunks. So what was the variable name? It was context only. Then query question is, I think the variable name was query or something. Yeah, the variable name for our query is query. So given the context for the query, answer the question. Then provide a concise answer. One more thing we could tell the LLM is, if you don't find the info in the context, do not guess. Say that the info is not found in the document, because this will help us from preventing the LLM, defaulting to its, it is trained to say something, right? It has some information about Microsoft and the world and its stock price and everything. But we don't want it to answer if the information is not present in the document, because that will be hallucination. Response equal to client.chat.completions.create. And then here we say model equal to one of the models. Any model is fine. GPT 4o mini. Then messages that we pass, messages equal to the role and the content is this prompt. And I think I'm having any client equal to OpenAI dot OpenAI, and then API key equal to user data dot get OpenAI key. And I already have it over here, so I should just enable it. So I had saved the OpenAI key here. So this is where you will have to save your own OpenAI key, and then answer equal to response dot choices dot message dot content, then print answer. We have to copy paste the, yes. So in the API key section for OpenAI, there will be one place where you have to just simply copy. There will be a copy icon. You have to just copy that. Print answer and then /n comma answer. So let's just see, let's run this to see if we are getting the actual answer. The answer that we are expecting is the answer for the question from 2024 to 2025. By how much did the revenue increase? There is some issue. Message does not exist or you do not have access. Excellent. So I just need to make sure that my API key is correct. Mm, GPT-4. Okay, there is a typo. Oh, yes, for sure. It should be 4.0. And yeah. There is another issue. Your account is not active. Please check. Okay, I think my account might have exceeded the billing, which is why I have another account. If anyone has reached this till this point, just let me know. If you have, I think my API keys might have expired. I will have to recheck this once, or my credits would have run out. Let me. I'll ask Gemini to change this part so that I can use Gemini API key. Change this code so that I can use Gemini API key. Just let me know if you have received any output yet. Like it will ask for a box where you have to enter the response, enter the query, and then it should produce a response. And Gemini API key I haven't set yet. So let me just set that. Okay, it should be named as Google API key, not Gemini API key. So okay. And API key is not valid. Excellent. This is very frustrating to not know which of my API keys have gone expired or credits ran out. Yeah. I think in the key I copy pasted the Google thing itself instead of, yeah. Let me just check this. I'm sure one of these keys work. Okay, I think this is a different issue. Gemini 1.5 Flash, I could just change it to 2.5 Flash because some of these have deprecated. So how about this? Okay, so the answer, okay, this is the answer that LLM gave. The context provides revenue figures, not profit figures. Therefore, the information on how much profit Microsoft made is not found in the document. Very good. So that is a good response. But then let me ask for revenue figures. So I will run starting from the query. Actually, I have one more block of code which you can directly copy paste. It's just for running the chatbot continuously, okay, without having to go back unnecessarily. Uh, Let me do that once. Okay, query what by how much did the revenue of Microsoft increase from 2024 to 2025? What is the 2024 to 2025 revenue increase? Okay, now I don't know what's the new issue. Explain error. Just let me know, guys, if any of you managed to get it correct so far. Should not be difficult. Encode is not a function. All right. I'm not sure because it was perfectly okay before I changed from OpenAI to Gemini. It should not matter what LLM I am using. That should not be an issue. The issue should be something else. Model needs to be changed instead of V2 to V. Oh, which V2? This one. I had earlier used V2, so I'm not sure why that is throwing an issue. But anyways, let us see. Okay, so now this is the vector representation of my query. Then these are the top retrieved chunks. Then this should be the re-rank chunks. Then these are my concatenated chunks, top three. And now this is my question to the LLM. The 2024 to 2025 revenue increase is 36 billion. So really good. I hope this is correct from the document. One simple thing you can do to make this into a chat bot instead of like a one-time chat thing is you can just, I have just one block of code, which I don't want to write from scratch. It's not fun, but just have this. I'll ask Gemini to change the last block of code. Change the last block of code so that I can use Gemini model. So if any of you manage to get an output, please feel free to share your screenshot of some actual difficult question. Ask some numerical question which should not be easily available. Okay, so now here I can ask the question uh, percentage increase revenue or in profit or in share price Let's see what comes. Unable to determine the intended type of dictionary. Oh, this is a different error. Oh, percentage sign is an issue. Is that an issue? Percent increase in share price. I would have guessed that is not an issue. Unable to determine intended type of dictionary. Let me just ask Gemini to have a look at this issue. So I had shared the link to the code once in the chat. So just copy the code if you want to. Try your own API key and just run it once. If you are getting the output, it'll be amazing. And try some other document where actual internet data is not available, because these models uh, already have a lot of real world info. Since txt document is working fine and able to retrieve correct values based on my query for, okay, so you used text loader, fine. Here in this, I can just type exit to just exit it. All right. But okay, for some reason, this conversation part is having an issue, but that is probably a temporary issue. Percentage increase in share price. Yeah, this issue is fixable. This we can fix later. But I think with this, we can move on to one last part. I have created an interactive exercise for you, but I don't want to go through the interactive exercise. That you can go through yourself. It's very simple. It's much simpler than the Google Colab code. But I want to walk us through some quiz. Okay, so just answer some of the questions in the chat. In the right select compress isolate framework, which operation does RAG primarily perform out of this ABCD? Fairly easy. This we have discussed in detail. It is basically selecting from the uh, memory, selecting from the storage or the database to be added into the context. What are the correct stages of RAG pipeline? ABCD. These are easy questions, okay? Just to make sure that everyone is on the same page. It's not to give you something amazing or anything. You first ingest, then chunk, embed, store, retrieve, generate. Fairly easy. You're building a RAG over markdown technical documents. Which chunking strategy would you use? Would you use fixed, page level, sentence aware, recursive? So mostly in this case, you will use recursive, because in markdown document by default, there is hierarchy. There are subheadings and headings, etc. So that structure you can follow if you use recursive. Fixed size chunking with chunk size 500 and overlap of 50 is processing a 1200 character document. What does it mean in terms of chunk size? How many chunks do you expect? Fairly easy question. So if the overlap was 0 and character size was, so first chunk will be 0 to 500, then it will be 450 to 950, then it will be 900 to 1400 up to 1400. But there should be 3 chunks. Then ChromaDB, this we have not discussed in detail, but basically you should know that ChromaDB also uses same built-in embedding model, which we just use, all mini LM L6 V2, and it runs without API key. What's the trade-off compared to OpenAI's this model? If you use ChromaDB's this model versus OpenAI's large model. Only issue is if the chunks are very similar or the the difference between the chunks are very difficult to capture, quality of the embeddings might not be very good, right? So obviously that's the trade-off. One of them will be faster, the other one will be more quality. Your RAG returns 3 chunks with distances between that and query. Basically, what is the refund policy? That's a query. These are the distances, which means what may be the case? So in general, it's hard to say without further context, right? Without more information, it's hard to say. But in general, if there is so much difference between first, second, and third, because 0.42 and 0.78 are different, I think mostly the first chunk is relevant. The other one, if you look at the percentage difference between these, there is one is almost the double of other, 0.42 and 0.78, and again 1.35. But yeah, it's very hard to interpret for sure. This BM 2.5 we haven't discussed in detail. BM 225 we haven't discussed in detail. Dense vector, yeah, this is an interesting question. We discussed about dense and sparse. So dense is the normal embedding with semantics. Sparse is the one which where words themselves are forming part of the each dimensions of the space. So if you are searching memory architectures and you find this chunk, how agents remember, why do you think in sparse keyword search this entirely is missed, whereas in dense it is not? In my opinion, B and D could be the answer. Like one is talking about sparse, the other one is talking about dense. So ideally, yeah, dense is using semantic similarity, and memory architecture and remembering, these two are semantically similar, right? So B, but D also technically you can say it's in this context it's the correct answer. How about this? If you are searching for ChromaDB vector database using both dense and sparse search, in which case do you think ChromaDB documentation will become the chunk number one? Think about the word ChromaDB. ChromaDB is a very rare word with very high, it will probably have a high IDF, inverse document frequency, because it's not a word that typically occurs very frequently. So it will help us easily identify the other chunk where that word ChromaDB is appearing. Similar to that quantum word, right? Okay, this we have not discussed reciprocal rank fusion because it's a little bit advanced, so that I will skip. Um, how about this? Your RAG system prompt says answer only using retrieved context. If the context doesn't cover the topic, say so. Why is this rule critical? We also did this when we wrote the code. Why is this needed? If we don't say this, what may happen? What may happen is LLM will try to give some answer, right? And that some answer will depend on its training. So we don't want that. We don't want LLM hallucinating and depending on its training data. We want it to depend on the RAG data. This also we can skip. Okay, how about this? A two-stage retrieval pipeline first retrieves 20 candidates with vector search, then re-ranks them with a cross encoder, just like we did, to select top 5. Why can't we use cross encoder directly on all chunks in the beginning itself? What's the issue with using cross encoder directly to get a, so that re-ranking need not be done in a second step? Because think about it, if there are large number of documents, you have that many number of pairs to look at. A query and a chunk is a pair, and that pair has to be passed through cross encoder. Same thing has to be passed through the next for the next pair. So running it on all the 1,000 or 10,000 pairs is very expensive. Then okay, so how about this? Your RAG system's context precision. So the definition of context precision is, if let's say you wanted to, I have written it here. If you wanted to retrieve something, how much percentage of what you want to retrieve has been retrieved? So context precision is how much of the retrieved context is actually relevant. Recall is the percentage. Recall is how much of the relevant information was successfully retrieved. Okay. So just remember this. Precision is if you retrieved 100 items, how many of them are useful? Recall is if you intended to retrieve some certain 100 items, how many of those 100 have been retrieved? Okay. Now with that in mind, if let's say your context recall is 95% and context precision is 40%, what would that mean? Does it mean that you are retrieving uh, only a fraction of what you need? Or does it mean that you're retrieving most of what you need, but you are also retrieving a lot of useless things? So context recall means 95% of what you should have retrieved, you have already retrieved, but you are also 60% additional things you are retrieving which are useless, which means maybe your top K is like you have defined K to be 15. That 15 you can reduce to 5 or something like that, right? Just so that only relevant items are present. This is regarding the write part, which we discussed. An agent writes task.md file listing its progress, key decisions, and blockers during a multi-step refactoring. In WSCI framework, what type of write is this? Is this memory? Is this file artifact, which is like an output from the file, or is it scratchpad or select? The main question is, first of all, this is select is RAG. Okay, so this is definitely not a select. This is a write operation. The only question is this something that is going into the permanent memory, or is this something that is temporary? This task.md, which lists the current progress or checklist or to-do list, are all for the current operation, which means it should be part of a scratchpad. It is not something which you will store for the upcoming task. It's for the current task. So it's a very ephemeral, short-lived memory thing, short-lived write. In the recommended RAG token budget allocation, approximately what percentage of total budget should be allocated to retrieve context? This is something which we vaguely discussed, but roughly it is 60%. The retrieved part should be maximum, roughly 60%. Remaining 10% will be for generation, and remaining 20% will be for all the other memory, knowledge, etc. Okay, this is another good question. You index your documents with OpenAI's text embedding 3 small model. So this is the like the sentence transformer, and you embed your query using Voyage AI's Voyage 3. Both are high quality embeddings, but what may happen? Will it work, or will it work imperfectly, or will it not work at all? The problem is these are two different embedding models, which means the vectors are living in different spaces, right? So your similarity search will not work. You need vectors living in the same embedding space. Okay, this is something very interesting. Anthropic's just-in-time retrieval is basically a concept where you retrieve things only when you need. For example, in our email tool, we retrieve a similar email to the current email thread required only when we encounter an email thread that is referring to something which we had talked about earlier, maybe 6 months back. So just-in-time retrieval basically only loads metadata. Okay, this is not something which we have discussed. It loads only metadata, and from the metadata, as and when the context feels like something is required to be retrieved, you will retrieve. So here you will try to shrink it as small as possible. Okay, this is something which we did not discuss in detail. How about this? Multi-query retrieval generates 3 variations of the same query. What is context engineering? And retrieves chunks for each. Why does this outperform single query? So the question is, you want to get answer to some question, but the same question you ask in 3 different ways. Why is this helpful compared to just asking one question in one way? Because when you are asking it in different ways, it will help us find semantically better chunks each of the times, because the choice of words will be different, but semantically it will all mean the same thing, right? So it's not like more retrieve chunks are always helpful or anything, because more retrieve chunks may still have junk chunks. We just saw that earlier, like 40% was the precision, 95% was the recall. But the thing is, when you ask it in many different ways, your semantic similarity to the relevant chunks, there is a higher probability that you will find it. How about this? Gemini has a 2 million token context window. So why do you need RAG? Just copy paste all the documents. What's the reason why people should not do this? Even if LLMs are giving you bigger and bigger context windows, simply because your context will degrade in quality, it will rot. This is something we have discussed many times. This is a big takeaway from this whole discussion. What happens if you increase your chunk overlap from 50 to 200 tokens? So for our 500 token chunk size, our overlap was 100. Here it was 50, and you increase it to 200. What may happen? Will there be no effect? Will there be an effect on quality? What may happen? So in general, what happens is, if you have more overlap, the boundary between chunk A and chunk B is overlapping. And if in both of the chunks, if you have relevant information, it's not like chunk 2 will be discarded. Chunk 2 will also be part of your retrieved chunks. So that is a good thing. So in general, your retrieved chunks will be of higher quality because the boundary is now, the context is provided for both of the chunks due to the overlapping tokens. But the problem is number of chunks will be so high. So in your, instead of 583 vectors, you may need maybe 1,000 or 1,500 vectors. So you are searching in a bigger space, right? Um, if overlapping is not there, think about it. Let's say there are no common words between sentence 1 and sentence 2, but sentence 1 is actually the preceding sentence of sentence 2. And maybe even if the words of sentence 1 and sentence 2 are different, maybe they are still a continuum of the same idea that is being discussed in the paragraph. So if zero overlap is provided, the context from the previous sentence is not available to the second sentence because of the zero overlap. If too much overlap is provided, if there is 100% overlap, there will be infinite number of chunks. If there is 90% overlap, there will be large number of chunks. So it's a fine balance between how much overlap you produce and how many chunks can you manage. A system has 50 plus tool descriptions consuming 8,000 tokens in the prompt. LangChain data shows that applying RAG to tool selection improves accuracy by 3x. How does it work? So the question is, instead of having all the descriptions of the tools stored in one place, you apply RAG to find the appropriate tool description whenever needed. And this is much better. And why is that? Because tool descriptions you may embed in a vector database, and using a RAG at any given point, you pick the top 3 or 4 or 5 tools required for that moment. Just like how in our email system, how we fetch top relevant 5 or 6 or 7 emails to be referenced for the current conversation that is happening. So that is the reason why RAG in general will be very helpful here. Now, last question, 25th question is not relevant. So in a RAG pipeline, stages 1 to 4, ingest, chunk, embed, store, run offline. This happens one time, and this is happening during indexing. But the last 4 stages happens during the request, each API request. Why is this separation architecturally important? The main thing is, as you might have seen, after creating the chunks, creating the embedding was the most time consuming part, right? When we ran the code, everything else was fast. The most time consuming part was embedding creation. So that should not happen in each query, because then the user will never use the chatbot. User will always feel frustrated. Okay, one more thing, offline stages handle private data while online stages only access anonymized data. Oh, that I am not sure how much that is true in general, because see, in offline stage, you are anyway providing all the PDF documents, right? And those PDF documents are chunked, and chunks are stored in the vector. And when you are asking the relevant query, those chunks are only fetched. So I don't think B is necessarily true. There is nothing about privacy or anonymity. You can implement some sort of anonymity if you want to mask certain data from appearing in the user side in the first place, but then you will be masking it from the data itself initially before you do chunking. So here it's about expense. All right. So that will be the end of it. So I recommend you to do 2 things. One is try chunking with different, there are different parts of the pipeline which you can change. The 25th question is not relevant. It's different question. We have not discussed it. So one thing you can do is change the data, the PDF ingestion pipeline, use something different, change the chunking type or chunking strategy, change the vector database, try maybe ChromaDB or something. Instead of Facebook AI search, try something else. And what more can you try? You can try some open source LLM. So there are different varieties you can try. And when this can be very helpful, when you implement the same pipeline to an industry where actually people are struggling to get relevant information, even in the presence of LLM, because all the information is present somewhere masked in documents or tutorials and stuff like that, just like OpenFOAM, because they have new releases, and it's often very difficult to find information with reference, because a RAG can provide references. It can say, hey, this is how it should be done, and here is the reference. And if they want to read the reference, they can go back to it, right? So just try a take home exercise of implementing the same thing. One more additional thing which you could do is, right now we did this in Google Colab. Same thing you can do where you have it running on a website. So you have a backend pipeline, you have a nice front end where people can log in and use. So that also you try, but you can try it with Google Colab. You can try it with Cloud Code. So today we have run pretty much for 2.5 hours without stop, and I thank you so much for staying back till now. We will meet again tomorrow. We will wind up the lecture here. And for any other questions, just drop me an email, hello@vizuara.com. We will meet tomorrow, same time, 9:30 a.m. IST. And one more thing, tomorrow we'll be discussing MCP. Yesterday's lecture, there was an issue in compilation. That's the reason why on YouTube, when I uploaded, there was some issue with the quality of the video. So it created some issue. Then I deleted it. I re-uploaded it. It should be public today by 3 p.m. IST. So you can just check it. I have added it in the free course dashboard. So thank you so much, everyone. See you again tomorrow. Take care. Bye.